This question is asked in gate 23 of instrumentation. This is from digital subjects and from sequential circuit topic. The question is, the table shows the present state qt, next state qt plus 1 and the control input in a flip-flop. Identify the flip-flop. So basically we are given with present state, next state. So based on present state, next state, input is determined. So what kind of table this represents? This definitely represents the excitation table, right? And we are supposed to find that this excitation table belongs to which of the following flip-flop. This is, students, a very standard data, right? The answer is T flip-flop for this, because like the pattern in the T flip-flop is both excitation table and the state table, they follow the XOR combination of first two column. In other words, XOR combination of this and this column will be this one. It happens in both excitation table as well as in the state table, only for the T flip-flop. So 0 XOR 0 0, 0 XOR 1 1, 1 XOR 0 1, 1 XOR 1 is 0. So definitely answer is option A, T flip-flop. This question is asked in gate 23 of instrumentation. This is from digital subjects and from logic gate topic. The question is, match the exclusive OR operation I to IV with the results P to S where X is a Boolean inputs. So this is again based on the standard XOR gate property. So we know that X XOR X, a variable XOR with itself, it always results 0. So 1 will be Q. A variable XOR with its complement, it results 1, right? And like a variable, if it XOR with 0, you get the same variable. So X XOR 0 is X, and a variable, if it XOR with 1, you get it is X complements. These are very standard data, right? A variable XOR with itself, it results 0. A variable XOR with its complement, you get 1. A variable XOR with 0, you get the same variable X. A variable XOR with 1, you get its complement. So you get X bar. So if you see the pattern is, so I is Q, second double I belongs to P, triple I belongs to S, and IB belongs to R, QPSR. So QPSR, if you check it, this is given in option D. So D is the right answer for this question. This question is asked in gate 23 of instrumentation. This is from digital subjects and from logic family topic. The question is, choose the fastest logic family among the following. This is a standard, standard data-based question, student. The answer is emitter coupled logic, right? So, in the logic family, you have studied these all things. CMOS logic, let's say, if I speak regarding the lowest power dissipation, it happens in the CMOS logic. So each family having their own merit demerits, but ECL family, emitter coupled logic family, this is the fastest logic family among all. Okay, it is a BJT based circuits only, so it is the fastest logic family. So answer is option B for this. This question is asked in gate 23 of instrumentation. This is from digital subjects and from K-map topic. The question is, the simplified form of the Boolean function f of wxyz with the minimum number of terms, smallest number of literals in each term is how much? I mean, basically, we are supposed to find that what is the minimized expression of this particular function among these options, right? So, like it can be solved using Boolean algebra or even K-map, but I believe in this case, rather than going through Boolean algebra by expanding these all, K-map will give us a very straightforward answer. So it's a 4-variable case. So I'm taking a 4-variable K-map. Okay. So there are 16 cells. So this side, let me take it for Wx. This is Yz. You get W bar X bar. You get W bar X. You get Wx. You get Wx bar. You get Y bar Z bar, Y bar Z, YZ, and YZ bar. So mean term 4, 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, then 12, 13, 15, 14. So this is what are the corresponding mean terms which are given in this function. I have plotted them in this map. Now we can do the grouping. I can see octet is not possible. Quad is possible. Definitely possible. This is one quad possible. My target is to cover all the mean terms. So this is also one more quad. Now it is being covered, right? So I think this is what is the minimal mapping. Now if I ask you what is the term corresponds to this, from row if you see x is constant, and from column if you see y bar is constant. Similarly for this, from row w is constant and from column y is constant. So if I ask you what is the answer of this f, it is basically the swap expression, which is xy bar, that is this term, or with this term wy, xy bar plus wy. If you see, this is given option C. So C is the right answer for this question. Very simple and straightforward question. Answer is option C. This question is asked in gate 23 of instrumentation. This is from digital subjects and from logic gate topic. The question is, for the given digital circuits A equals to B equals to 1. Assume that AND or NOT gates have propagation delay of 10, 10 and 5 nanoseconds respectively. All lines have zero propagation delay. Given that C equals to 1 when the circuit is turned on, the frequency of steady state oscillation of the output Y is how much? So we are supposed to find what is its corresponding frequency. So it is given clearly that A equals to B equals to 1. So I am making B value 1, A value 1. And if you see, this is Y, so this is basically Y. If Y is the input, it's a NOT gate, its output will be Y bar. If 1 is the input, 1 complement is 0. So 0 or with Y bar is basically Y bar, and A is 1 means this is also 1. So now the input to the AND gate is Y bar and 1, so its output is basically Y bar. If you observe here, students, so that this is actually Y, but by finding its corresponding expression, we are getting Y equals to Y bar, right? Because this we are getting as Y bar and this is given as Y. So what is happening? Y equals to Y bar. So whenever Y equals to Y bar, what happens? You remember the application of ring oscillator, or which is square wave generator. When a variable is equals to its complement, you get this square wave because the output is unstable. So if it is 0 now, after some time it will be 1. After some time it will be 0. So that kind of behavior it happens. Alright. Now the point is, but Y equals to Y bar. Okay. So what is the meaning of it? Now let us assume that initially that this Y equals to 0. So let us assume that initially Y equal to 0. So if Y equal to 0 now, after how much time it will be 1? Because we know if it is 0, after some time it will be Y complement, that is 0 complement will be 1. So what is that time lapsed? So that depends on the delay involved in the circuits. Now you see that the delay information, if we write it over the gates, AND gate delay is 10 nanosecond. So this is your 10 nanosecond. OR gate delay is also 10 nanosecond. And the NOT gate delay is 5 nanosecond. So this delay is 5 and this delay is 5. Now see, students, now initially if I assume that output Y equal to 0, so this 0 will be coming here, right? So it will be passing this NOT gate. So the time lapse is 5 nanosecond to get this output, and then the time lapse here is 10 nanosecond. So if you are assuming that the initial output is 0, you get the corresponding signal here after 15 nanosecond. The delay here is 5, the delay here is 10. 5 and 10, 15, and again there is one more gate, 15 and 10, 25. So if the present state is 0, after 25 nanosecond, you will be getting this corresponding new output. Okay, so now it will be 1. So this one will be again processed. It will be again passing through 5, 10, 10, 25. It will be again 0. So this 0, 1, 0, 1 pattern will continue in every 25 nanosecond interval. Now if I ask you to plot the waveform of this output, so it will be 0 initially we said for how much time? For 25 nanosecond, because 5, 10, 10. Always 5, 10, 10. So in these all things will not matter, student, because these are constant, right? 1, 1, they are fixed. So it really doesn't matter, right? Because this will be constant. Because if these two are constant, so this input and this inputs are constant. So whatever changes are happening, that is being reflected in this path only. So this path delay we are considering 5, 10, 10. Okay. Now don't add that 10, 10, 10, not like that. Okay, because this is fixed. So if I am assuming output is 0, so this is staying for 25 nanosecond. Then after 25 nanosecond, so that become 1. So this one is staying again for 25 nanosecond. Again after this it will be 0 for another 25 nanosecond, and again it will be 1, and so on and so forth. So this is how the waveform you will get at the output, I mean the waveform of Y. So we are supposed to find the frequency, right? So the time period, if you check, the time period is coming as 50 nanosecond. If the time period is 50 nanosecond, f is equals to 1 by 50 into 10 raised to power minus 9. If you check it out, so this happens to be 20 megahertz. So the frequency is 20 megahertz. They're asking in what units? Okay, so options are given, right? So yeah, it is 20 megahertz. So answer is option A for this. This question is asked in gate 23 of instrumentation. This is from digital subjects and from sequencer circuit topic. The question is, in the circuit zone, the initial binary content of shift register A is 1101 and that of shift register B is 1010. The shift registers are positive edge triggered and the gates have no delay. When the shift control is high, what will be the binary content of shift register A and B after 4 clock pulses? So this diagram is enough. So we are supposed to find the content of this register A and B after 4 clock pulses, right? So this is, student, the usual shift register problem what we get, but one additional register is attached here. So anyway, so no problem. So we'll be proceeding this in the as usual normal methods. So let me make a table here, like how we find the counting pattern of a register, right? So this is the first column is clock, next column is inputs, and okay, so this is shift register A. So input means this is what I mean by inputs. Okay, so what is this inputs? So this is, let's say, Q0, this is Q1, this is Q2, this is Q3. So if you see, it is Q0 XOR with Q2 complement, right? Because this is your Q0, this is your Q2, so this is your Q2 complements. So the input to the XOR gate is Q0 and Q2 complements. Q0 XOR with Q2 bar. So input is equals to Q0 XOR with Q2 bar. And because it is shift register A, so let me attach this suffix A. Alright. Clock input and then the shift register A, so let us write its corresponding flip-flop outputs. So it is your Q3A, then your Q2A, then your Q1A, then your Q0A. Similarly, for the next register, you have your Q3B, and then you have Q2B, then you have Q1B, and then you have Q0B. All right. So clock number 0, we haven't given any inputs. So it is 1101. If you see the initial content of shift register A, it is 1101, 1101. And the initial content of shift register B is 1010, 1010. Okay. So by observing the circuit diagram, so we figure it out like what is the input. Okay, I mean input in the sense what is the output of this XOR gate. So by observing notation, it is Q0A XOR with Q2 complement A. Now, how does this data transfer happen, student? Here, if you observe this one carefully, how the data transfer will happen? See, whenever you are giving the clock, then this clock is simultaneously getting applied to this register and this register. So under operation, the shift control will be made 1 and this is clock. So this is a clock. So this clock, whenever you are applying the clock, this clock is getting applied to shift register A and shift register B simultaneously. So the data shifting, it is going to happen simultaneously. So how does the data shifting will happen then? How does the data shifting will happen? See, so in the normal way, okay, so whenever, let's say a press input is coming to this one, the output of the XOR gate, so it will be pushed. It will be pushed the way it happens, and in the simultaneously, whatever the bit will be available here, it will be getting pushed to this register because the LSB of this shift register A is connected to the MSB of shift register B. So whenever you are applying the clock, how the data movement will happen? This way it is going to happen. So let's say presently it is here. Okay, so this one will be coming here. This one will be coming here. This 0 will be coming here. This one will be coming here. Like that the pattern will continue. So let us see here. You will understand clearly. So first thing is, so what is this Q0A and Q2 complement A? Q0A is 1 and Q2 complement. Okay, so Q2 is 1. So 1 complement is 0. So Q0A is 0. Sorry, Q0A is 1 and Q2A complement is 0. So 1 XOR 0 is basically 1. And now we'll be giving the first clock. Is that fine? Q0A. So this is your 1 and this complement is 0. So 1 XOR 0 is 1. So now we are giving the first clock. So if you give the first clock, what is going to happen? This one will be coming here. This one will be coming here. This one will be coming here. This 0 will be coming here. Now what is going to happen, students? What is going to happen? Now as I said, so you see here. So this will be coming here. So how do you represent it here? So this one will be coming here. Again the same pattern. So this one will be coming here. If this one has come here, so what is going to happen then? So I mean this has come here. So these 3 bits will be pushed by 1 bit. Then it will be followed by 1 0 1. 1 0 and 1. Have you understood or not? So this one is pushed here. So if this one is pushed here, so the this has come here, let's say, and then these 3 bits will be pushed by 1 bit like this. So 1 followed by this 1 0 1 like that. Fine. Now let us again evaluate the input and we'll give the second clock. So Q naught A is 0 now, and Q2 complement, if I find it out, it will be 1 complement is 0. So 0 XOR 0, it will be 0. Now you give the second clock. If you give the second clock, so this 0 will be coming here, this one will be coming here, this one will be coming here, this one will be coming here, this 0 will be coming here. So now this 0 has come. So now what is going to happen? These 3 bits will be pushed by 1 place. So 0 followed by, it will be 1, 1 and 0. Again we will find the input. Q naught A is how much? This is how much? 1, and Q2 A complement is 0. 1 XOR 0 is your 1. You give the third clock. So you get here 1, you get here 0, you get here 1, you get here 1, you get here 1. Now these 3 bits will be pushed. So you get it is 0 1 1, 0 1 1. Similarly, so again we'll be finding this Q naught A is 1 here, and this Q2 A complement will also be 1. 1 XOR 1, it will be 0. So this is 0. Now you give the fourth clock. So this will be 0, this will be 1, this will be 0, this will be 1, this will be 1, and now these 3 bits will be pushed by 1 bit. So 1 0 and 1. So 4 clocks we have given. So that is what you are supposed to find. What is the content of shift register A and shift register B after 4 clock? So after 4 clock, shift register A is containing 0 1 0 1. This is what is the content of shift register A, and shift register B is containing how much? 1 1 0 1. 0 1 0 1 and 1 1 0 1. 0 1 0 1 and 1 1 0 1. If you see, this is given in option C. So C is the right answer for this problem. So right, so just only one thing we have to observe is how the data shifting is going to happen to shift register B. So whenever a clock pulse is applied, so whatever the output will be there in this XOR gate, so that will be pushed by 1 bits. So simultaneously this MSB bit will be pushed to this LSB, and these 3 will be placed by 1 positions. So that pattern we have followed, and we are getting the answer as option C. Okay, so answer is option C for this.